Good evening, everyone. Good evening, good evening. I welcome you all again to the NEET Elite. Hoping that you guys are doing great, having the good time. Well, people, you can let me know in the chat box if I'm audible and visible to everyone. Hello, Aradia. Hi, Afshan. Hi, Afreen. Hello, Arzu. Hi, John Peter. Hi, Lekashri. Hi, Dinesh. Hello, Gayatri. Hi, Sahana. Hello, Saranya. Hi Karthik, welcome everyone, welcome to the session, Let me know in the chat box if I'm audible and visible to everyone, yes. Let me know, I'm doing good Afreen, I'm doing good. I'm doing great, John Peter. Perfect. So people, as you all must be knowing, today it's going to be the third session from the chapter solution, right? In the last session, we talked about something called as Rawls law. We discussed about the Rawls law in detail, yeah. And in the today's session, we are going to do something called as ideal and non-ideal solutions, right? Perfect. So we are exactly going to start from the basics, and we'll be covering this ideal and non-ideal solutions in detail in the today's discussion, right? Perfect, guys, perfect. So for the ones who are new to the channel, let me introduce myself. My name is Wassim Sir, and I'll be your chemistry master teacher writer on this channel, yeah? And for the ones who have not liked the video yet, please do like the video, share the video and subscribe the channel as well. And do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking right here on this NEET Elite channel. Okay, Gurnoor 2022 batch, I'll be starting next week, okay? Next week, I'll be starting the 2022 batch, right? Perfect. All right, guys. So you can let me know in the chat box if you guys are super duper excited about the session. Let me know in the chat box with the thumbs ups, right? Let me see the josh of the session first. Then only we'll be starting, yeah? Right? Okay, wonderful. Great, guys. Perfect. So let's move on. Let's get started with the today's discussion, in which we'll be talking about something called as ideal and non-ideal solutions, right? So first of all, guys, I hope you remember states of matter, the gaseous state which we discussed. I mean, we have finished the states of matter, right? How did we define the ideal gas there? We defined the ideal gas as it is a gas which, any gas which follows the ideal gas equation. That's what we call as ideal gas, if you remember. In the same way, I'm going to define the ideal solution yet. Okay? Understand what I'm going to do over here. Let me mark the heading as ideal solution first, yeah? Ideal solution. How do we define this ideal solution? Let me write its definition first, then I'll make you understand exactly what this ideal solution is all about, right? See, guys, the solution which obeys Rawls law, the simplest definition I'm writing, okay? That solution which obeys the Rawls law under all compositions is what we call as ideal solution. Now the point is, what is meant by this? First of all, as per the definition of ideal solution is concerned, any solution which obeys the Rawls law under all compositions. That's what we call as ideal solution, yeah? And any solution which does not obey the Rawls law under all compositions, that's what we call as non-ideal solution. Now the point is, what can we get from this definition? Understand properly what I'm going to say, okay? I'm exactly going to start from the basics. For example, I'm taking a container right here. This is the container which I'm taking, okay? Right? See, guys, what I'll be doing. This is the container which I took, and in this container, I'm keeping a solution which consists of volatile liquids A and B, right? I have got a solution in this container which contains volatile liquids A and B, right? So first of all, I'm going to connect this container to the manometer. If you remember in the first discussion, we have talked about this as well. I'm connecting this container with the manometer over here like this. Yeah, this is the manometer which I have kept over here. And this is the stopcock which I have used over here, right? This is the stopcock which I'm using. And in this manometer, what do we have? We have got mercury filled in this manometer, correct? Since the stopcock is closed right now, so the level of mercury in both the limbs right now will be same, yeah? Now people, since the solution contains the volatile liquids A and B, since A is volatile as well as B is volatile, so over here you'll be having the vapors of both A and B, correct? You'll be having the vapors of both A and B right here in this container, yeah? Now people, understand one thing. If I'll remove the stopcock, what is going to happen? The mercury in the left limb, it will start going down, and the mercury in the right limb, it will start coming up, due to which there will be height difference created, right? There will be height difference created between the mercury in both the limbs, right? Correct? There is, for example, height difference created like this between these two limbs, yeah? Okay, and let's assume this height is equal to h, correct? Now people, by using this manometer, what I'm doing is I'm calculating the total vapor pressure of the solution over here. And the vapor pressure of this solution which I'm determining right here by using this manometer, that's what I call as experimentally determined vapor pressure. That's what I call as simply experimentally determined vapor pressure. Or I call this as the actual vapor pressure of the solution. Actual vapor pressure of the solution, yeah? So first of all, be careful with the terminologies. Whenever I say actual vapor pressure of solution, one thing should strike your mind. That means I'm talking about the vapor pressure of the solution which I have calculated experimentally by using this manometer over here, right? Okay. So people, actual vapor pressure of the solution, or you can call it as the experimentally determined vapor pressure of the solution. This is the vapor pressure of the solution which I measure experimentally by using the manometer, right? Now, in the last session, if you remember, we talked about something called as Raoult's law, yeah? As per Raoult's law, I can calculate the vapor pressure of this solution as well, yes? And I can say total vapor pressure of the solution as per Raoult's law is simply going to be equal to P naught A multiplied by chi A. It's going to be equal to P naught A multiplied by chi A plus P naught B multiplied by chi B, correct? This is again, by using this equation, I'm again calculating the vapor pressure of the solution, total vapor pressure of the solution. And whenever I'll be calculating the total vapor pressure of the solution by using the Raoult's law, that vapor pressure I call as the theoretical vapor pressure. Yeah, this is something which I call as theoretical vapor pressure of the solution. Correct? I'm sure you're clear with the two terminologies. One is actual vapor pressure of the solution, which I'm calculating by means of this instrument manometer. One is theoretically determined vapor pressure of the solution, which I'm calculating by using the Raoult's law, right? Well, people, there are certain solutions in which the actual vapor pressure and theoretical vapor pressure of the solution comes out to be same. There are certain solutions in which actual vapor pressure and theoretical vapor pressure comes out to be same. And those solutions in which theoretical vapor pressure and actual vapor pressure of the solution comes out to be same, we call those solutions actually as ideal solutions. Yeah? And similarly, I can define the non-ideal solutions, those solutions in which the theoretically determined vapor pressure is not equal to the actual vapor pressure. Okay, that's what I call as a non-ideal solution. Let me know in the chat box if you just got the idea of what are ideal solutions and what are non-ideal solutions. Ideal solutions are the ones in which the actual vapor pressure of the solution, which we calculate experimentally, and the theoretically determined vapor pressure of the solution, which we calculate by means of Raoult's law, okay, right, which we calculate by means of Raoult's law, that comes out to be same. And any sort of solution in which actually determined vapor pressure and theoretically determined vapor pressure comes out to be same, we call those solutions as ideal solutions, right? And any solution in which the theoretically determined vapor pressure and experimentally determined vapor pressure comes out to be different, we call them as the non-ideal solution, right? I'm sure this is clear to everyone. This is the basic definition of it, correct? Now, people, let's try to analyze this ideal solution a bit more in detail, okay? So first thing you got to know about the ideal solution. What is that? Let me write it in the form of point over here. I'm writing experimentally determined vapor pressure of the solution is equal to the theoretically determined vapor pressure of the solution, right? Which solution I'm talking about right here? I'm talking about the ideal solution, number one. Number two, understand properly now, okay? See guys, there are some parameters in this ideal solution which you need to remember, okay? And which you need to understand as well. What are those parameters for the ideal solutions? Understand properly what I'm going to say. Let's assume this is one container which I've taken over here. And in this container, I have got a volatile liquid A. This is the volatile liquid A present in the container. And over here, what you'll be having only the vapors of A, and whatever is going to be the vapor pressure right here, that's going to be due to A, which I'm calling as P naught A. P naught A is the vapor pressure of A in pure state, yeah? Now similarly, what do I have? I've got one more container over here. And in this container, I'm keeping one more volatile liquid B, yeah? This is volatile liquid B, correct? So over here, you'll be having vapors of B. So whatever is going to be the vapor pressure, that I'm representing by P naught B, right? So P naught B is the vapor pressure of B over here in pure state. Now what am I doing is, I'm simply mixing them up, yeah? I'm simply mixing these two liquids up, which are both volatile in nature. So what I'll be getting right here, I'll be getting a solution containing A and B. Solution containing volatile liquids A and B over here, correct? Now at the same time, right here in this space, we'll be having the vapors of A and B, okay? And the total vapor pressure of the solution, I'm representing by PT. And as per Raoult's law, your PT is equal to P naught A multiplied by chi A plus P naught B multiplied by chi B, correct? So people, the solution which I got over here, okay, the solution which I got over here, if the solution has to be ideal, then the experimentally determined vapor pressure should be equal to the theoretical vapor pressure, which is calculated by means of Raoult's law. Then only I can call this solution as the ideal solution, right? Okay, or you can something like this, the observed vapor pressure, which I calculate by means of the manometer, right? The observed vapor pressure, the actual vapor pressure, it should be equal to P naught A multiplied by chi A plus P naught B multiplied by chi B. Then only I can call the solution right here as the ideal solution, yeah? Point number one. Point number two, guys, understand. In case of ideal solutions, understand properly. See, let's assume the volume of this liquid A is equal to V1. The volume of this liquid B is equal to V2. Let's assume the resulting volume of this solution over here I'm representing by VR. Remember, in case of ideal solution, the resulting volume of the solution is equal to V1 plus V2, okay? Remember, this is one characteristic feature of your ideal solutions. Resulting volume of this solution will be always equal to V1 plus V2, okay? Or I can write it like this as well. We say delta V mixing. Delta V mixing in case of ideal solution, it is equal to 0, correct? Delta V mixing in case of ideal solutions is equal to 0. How can we say delta V mixing in case of ideal solutions is equal to 0? Since we know delta V means change in volume. Change in volume means final volume minus initial volume. What is the final volume? That is VR. What is the initial volume? That was V1 plus V2. If V1 plus V2 is equal to VR, that means VR minus V1 plus V2 comes out to be 0. So I can say delta V mixing in case of your ideal solution, it will be always equal to 0, correct? This is one more parameter, okay? Now talking about one more parameter about this ideal solution over here, understand. See, over here in this liquid A, we have got the interactions between A and A particles, right? In this liquid, since this is basically the liquid A, which contains AA interactions, this is your liquid B, which contains BB interactions, yeah? And this is the solution, which will be now containing AB interactions, right? Remember, in case of ideal solutions, the force of attraction between A and A will be equal to the force of attraction between B and B, will be equal to the force of attraction between A and B, okay? Remember, in case of your ideal solutions, the force of attraction between AA molecules will be same as that of force of attraction between BB molecules, will be same as that of force of attraction between AB particles as well. That's why your delta V mixing comes out to be 0 over here, right? Okay, that's why the final volume of the solution will be equal to volume of liquid A plus volume of liquid B over here, correct? Okay. Now people, few more features about this ideal solution. But before that, let me know in the chat box if it is clear till here or not. Let me know in the chat box if it is clear till here or not, so that we can move on. Yeah? Let me know in the chat box. Correct? So till now we got to know, in case of ideal solutions, the experimentally determined vapor pressure is equal to the theoretically determined vapor pressure. And at the same time, we got to know delta V mixing in case of ideal solutions is equal to 0. And we got to know the force of attraction between A and A is equal to force of attraction between BB is equal to the force of attraction in AB, correct? Right? This is something which we got to know till now. Now people, one more thing which I want to share with you over here. What is that? See, I'm sure you would have written everything till here. Yeah? Now, in case of ideal solutions, we say delta H mixing is equal to 0. We say in case of ideal solutions, the delta H mixing is equal to 0. First of all, if I consider liquid A, yeah? Which all interactions do I have in liquid A? I've got only AA interactions in liquid A. Similarly, in liquid B, we have got only BB interactions. And when I'm mixing them up, I'm getting the AB interactions over here, okay? Since the force of attraction everywhere is same, understand what is happening basically when I'm mixing them up. When I'm mixing them up, in order to form this force of attraction, in order to form the force of, in order to get the force of attraction between A and B, what has to happen? First, this force of attraction has to break, this force of attraction has to break, then this A and B will start interacting and they will form AB, right? Okay, so first of all, this bond has to be broken down, this bond has to be broken down, and at the end, this bond has to get formed over here, correct? And we know bond formation is exothermic, right? Bond breakage is endothermic. You all must be knowing that. Over here, first of all, this bond has to be broken down. So energy is required to break this bond. So I can say delta H in order to break AA bond, delta H in order to break AA force of attraction, it's going to be positive because it's endothermic in nature. Similarly, I have to break this bond as well. So it's again endothermic. So delta H to break BB bond, it's again positive, right? I have to supply energy. I mean, energy is to be absorbed in order to break this bond. Yes. And once these bonds are broken, once these force of attractions are broken, what is going to happen? Bond formation will take place. And bond formation is the exothermic process. So delta H for AB comes out to be simply negative over here. Correct? Remember, in case of your ideal solutions, delta H mixing is equal to 0. Delta H mixing is equal to 0. What does that mean? That simply means the force of that simply means the energy required to break the bonds is equal to the energy released after the bond formation. So whatever energy is absorbed over here to break these bonds, same is the amount of energy which got released once this bond got formed. So in general, in total, I'll say delta H mixing over here will be 0, okay? There is no net absorption of energy. There is no net release of energy because what has happened over here, the energy which was required to break these bonds, same is the energy which you are getting once this bond is getting formed. So you can clearly say your delta H mixing of the ideal solutions, it's always taken to be 0, okay? This was the next point, which I'm sure is clear to everyone. You can let me know in the chat box if it is clear to everyone fast. You can let me know in the chat box. You can let me know in the chat box. Remember from now onwards, delta H mixing for the ideal solution is equal to 0, yeah? Let me know fast in the chat box. Or rather, it's okay, you can watch it. Perfect, guys. Now, next point. Next point about this ideal solution. We say in case of ideal solution, delta S mixing is positive. Delta S mixing is positive. What is meant by this term? Delta S mixing is positive. That means during mixing, entropy of the system is increasing. Entropy of the system is increasing, which you can clearly see. Right here, we have got only a liquid, right here in this container we have got liquid A, so there'll be only molecules of liquid A over here. You'll be having liquid A particles only. Over here you'll be having liquid B particles only, but over here you will be having A particles and as well as B particles in this solution, correct? So can I say when I have added these, when I have mixed these two solutions over here, the net solution which we got, its randomness of the particles in the net solution would have got increased, and increase in the randomness leads to increase in entropy. Yes, so I can clearly say during mixing over here, what is happening to the entropy of the system? Entropy of the system is increasing. Right here you can clearly say you had only particles of A. Right here you had only particles of B. When I mixed them up, what did I get? I got the solution which contains A particles as well as B particles. So I can clearly say the randomness over here, it would have got definitely increased, okay? And if randomness increased, that means the entropy is increased. If the entropy has increased, I can clearly say delta S mixing will be positive over here, correct? What is delta S mixing basically? That is final entropy minus initial entropy. If final entropy of the solution is greater than the initial entropy of the solutions, then I can clearly say this value will come out to be positive over here. Let me know in the chat box if it is clear to you or not. Yeah? Right? I'm sure it's clear to everyone, correct? Now people, one more point about this ideal solution. That is, we say delta G mixing is negative. Delta H mixing is negative over here when we get the ideal solution, right? See guys, how can I conclude this? You know, delta G is basically, as per thermodynamics, delta G is equal to delta H minus T delta S, correct? Right? Since delta H, in case of delta H mixing for the ideal solutions, is equal to 0, so I can clearly say your delta G mixing will come out to be minus times T delta S. This delta S is positive, so the overall sign of this comes out to be negative. So we clearly say delta G mixing in case of ideal solution is equal to negative, right? Remember this as well. So let me write all these points in nutshell over here. Let me write all these points in nutshell over here. In case of ideal solutions, first of all, experimentally determined vapor pressure of the solution comes out to be equal to the theoretically determined the vapor pressure of the solution. Yeah? The interaction in liquid A is same as that of interaction in liquid B, is same as that of interaction in AB, okay? The next point which we discussed was that delta V mixing in case of ideal solution, it is equal to 0, okay? I can clearly say in case of ideal solution, delta H mixing is equal to 0, correct? And at the end, we saw one more thing, that was delta G mixing, that comes out to be negative for the ideal solutions. And at the same time, we saw one more thing, that was delta S mixing of the system, okay? It comes out to be greater than 0 right here in case of ideal solutions. Yeah? Lekashri, you can just refresh your page. It will be automatically clear to you. Let me know in the chat box if it's clear to everyone. Yeah? Arshal, I'm doing great. Let me know in the chat box if it's clear to everyone. Right? Let me know fast. Okay? Wonderful, guys. Great. Now let's talk about something called as non-ideal solutions, yeah? Let's talk about something called as non-ideal solutions. So first of all, you can clearly say what are non-ideal solutions, yeah? Non-ideal solutions are the ones which do not obey the Raoult's law under all compositions. Point number one. Now the point is, how can we understand this? First of all, non-ideal solutions are the ones in which experimentally determined vapor pressure is not equal to the theoretical vapor pressure which is calculated by means of Raoult's law. Theoretically determined vapor pressure means I'm talking about the vapor pressure of the solution which is calculated by means of what? By means of the Raoult's law. Correct? Okay, this experimentally determined vapor pressure is the vapor pressure of the solution which we calculate by using the instrument called as manometer, correct? Okay, so in case of non-ideal solutions, first of all, we say the experimentally determined vapor pressure calculated by means of a manometer is not equal to the theoretically determined vapor pressure which is calculated by means of Raoult's law. Or I can clearly say the observed vapor pressure of the solution, that means I'm talking about the actual vapor pressure of the solution, right? That means I'm talking about the actual vapor pressure of the solution, the experimentally determined vapor pressure of the solution. It won't be equal to P naught A chi A plus P naught B chi B, right? P naught B chi B. Okay, that solution in which the actual vapor pressure won't be equal to the theoretically determined vapor pressure, which was calculated by means of Raoult's law. We call that solution as non-ideal solution. We call that solution as non-ideal solution. Now, people, there are two things which can happen over here. Okay, see, the first case which I can generalize over here, the first case, if the observed vapor pressure, that means the actual vapor pressure, okay, it can either be greater than P naught A chi A plus P naught B chi B. It can either be greater than P naught A chi A plus P naught B chi B, or the actual vapor pressure, which I call as observed vapor pressure, it can be less than P naught A chi A plus P naught B chi B. These are the two cases which can arise in case of what? In case of the non-ideal solutions, correct? Right? These are the two cases which can arise in case of non-ideal solutions. Okay? Point number one. If the actual vapor pressure of the solution, it can be either greater than the theoretically determined vapor pressure of the solution, or the actual vapor pressure of the solution can be less than the theoretically determined vapor pressure of the solution. Okay? That solution in which experimentally determined vapor pressure comes out to be greater than the theoretically determined vapor pressure of the solution, we say that non-ideal solution shows positive deviation from the Raoult's law. We say that that non-ideal solution shows positive deviation from the Raoult's law. Yeah, and that solution in which, that non-ideal solution in which the actual vapor pressure, the observed vapor pressure comes out to be less than that of theoretically determined vapor pressure, we say that non-ideal solution, it shows negative deviation from the Raoult's law. Okay, so in case of your non-ideal solutions, we have got two things. One, non-ideal solutions showing positive deviation from the Raoult's law, another non-ideal solutions showing negative deviation from the Raoult's law, correct? Okay, now let's try to analyze these non-ideal solutions with positive and negative deviation in detail. I'm sure you just got the concept of what are non-ideal solutions. In short, remember one thing, non-ideal solutions are the ones in which the experimentally determined the vapor pressure of the solution comes out to be different than that of the theoretically determined vapor pressure of the solution, which is calculated by means of Raoult's law. Yeah? Okay. Now, two cases can arise in case of non-ideal solutions. Either the experimentally determined vapor pressure of the solution will be greater than the theoretically determined vapor pressure. Okay. We say that solution shows positive deviation, right? Similarly, one more case can arise in which the experimentally determined vapor pressure of the solution comes out to be less than that of theoretically determined vapor pressure of the solution, and we say that solution shows the negative deviation, correct? Rajesh, after this chapter, we'll be doing the atomic structure, bro. Okay, now people, let's try to understand this a bit more in detail, okay? So first of all, I'm going to talk about the non-ideal solution. I'm going to talk about the non-ideal solution showing positive deviation from the Raoult's law. Okay, let's try to analyze this. The first thing, understand. This is, for example, a container which I have. In this container, I have got only volatile liquid A. So the vapor pressure of this A is going to be represented by P naught A. P naught A is the vapor pressure of this liquid A when present in pure form, right? Similarly, I've got one more volatile liquid B over here, which I'm calling as volatile liquid B, okay? So over here, you'll be having the vapors of B only, and we call the vapor pressure of B in pure state as P naught B, right? Now, what am I doing over here is, I'm mixing them up, yeah? I'm mixing them up. After mixing, I get a solution, and this solution is basically of A and B. This is the solution of A and B over here. So right here, you'll be having the vapors of both A and B, yeah? You'll be having vapors of both A and B, and the observed vapor pressure of the solution I'm representing by POBS, right? Which is basically determined experimentally by means manometer. And the theoretically determined vapor pressure of this solution I'm representing by PT, okay? Which is calculated as per Raoult's law, which is going to be equal to P naught A chi A plus P naught B chi B, correct? P naught B chi B. Correct? Now, first of all, in case of non-ideal solutions, we know observed vapor pressure, or you can say actual vapor pressure, or you can say the experimentally determined vapor pressure. It won't be equal to the theoretically determined vapor pressure. Correct? In case of non-ideal solutions, right? And this is the case which shows positive deviation. Okay? I mean, this is the case which I'm calling as non-ideal solution showing positive deviation. As I told you, in case of non-ideal solution showing positive deviation, the observed vapor pressure will be greater than the theoretical vapor pressure. Or you can say it like this: the observed vapor pressure, which you call as actual vapor pressure, it will be greater than P naught A chi A plus P naught B chi B. Yeah? Okay? In this solution, which is showing the positive deviation, I can clearly say the actual vapor pressure of the solution, the observed vapor pressure of the solution will be greater than P naught A chi A plus P naught B chi B. Okay? Now the reason is, why is it happening? Why is it happening? What can we understand from this thing? See, the experimentally determined vapor pressure, which is what I call as observed vapor pressure of the solution, it is greater than this value. It is greater than the theoretical value. What can we conclude from here? We can conclude something from here like this. We can say something like this, that the actual vapors right here, in this container, the amount of actual vapors in this container will be greater than the expected vapors in this container. Yeah? That is why your actual vapor pressure comes out to be greater than that of theoretically determined vapor pressure. Correct? Yes? Let me know in the chat box if you're getting it. Right? What I'm saying over here is, in case of non-ideal solution showing positive deviation, the experimentally determined vapor pressure will be greater than the theoretical vapor pressure, which is calculated by means of Raoult's law. So we can clearly say something like this: the experimentally calculated amounts of vapors will be definitely greater than the expected amount of vapors over here. Now, when is that possible? Experimentally determined vapors will be more in amount. That is only possible if AB interactions will be less than that of AA and BB interactions. Yeah. So this thing is only possible if AA interactions and BB interactions will be less than that of AB interactions. If AB interactions are less, I'll say AB particles will be far from each other, right? If they are far from each other, the force of attraction between them will be less. Their escaping tendency will be more, due to which the experimentally determined vapors over here will be more than that of expected vapors, which I was expecting as per the Raoult's law. Yeah? Correct? So the first thing which I want you guys to take a note of, correct? The AB interactions in case of this solution will be less than that of BB and AA interactions. Okay, that's why the amount of vapor generated over here will be more, due to which experimentally determined vapor pressure will be greater than the theoretically determined vapor pressure as per Raoult's law. Correct? Okay, right? Let me know in the chat box. Let me know in the chat box if it is clear. Let me know in the chat box if it is clear to everyone. Let me know fast. Yeah? See guys, it's simple. This is the solution which I got over here, which I'm calling as non-ideal solution showing positive deviation. For example, I'll be having an ideal solution right here. Let's say this is one ideal solution right here, correct? This is the ideal solution of A and B. If this is the ideal solution, the total vapor pressure, or you can say the observed vapor pressure of the solution, that will be equal to P naught A chi A plus P naught B chi B, correct? Right? Okay. This is the vapor pressure of the solution when this solution will be ideal in nature. Yeah? This is the vapor pressure of the solution when this solution will be ideal in nature. But right now we have got that solution which is showing negative deviation. Sorry, positive deviation. Okay? Positive deviation means the observed vapor pressure is greater than that of theoretical vapor pressure. The observed vapor pressure will be greater than that of that vapor pressure of the solution, which is calculated theoretically by means of the Raoult's law. Which is possible only if the amount of vapors generated over here in this solution will be more than that of ideal solution. Okay, if the amount of vapors generated over here will be more than that of ideal solution, that means the vapor pressure over here will be definitely, the actual vapor pressure will be definitely more than that of theoretically determined vapor pressure as per Raoult's law. Yeah. So I can say vapor pressure of this non-ideal solution showing positive deviation will be definitely greater than the vapor pressure of the solution which is ideal in nature. Correct? You can say it like this as well. Okay? Very simple. So I can clearly say the amount of vapors over here will be definitely more. And how can we explain that? We can explain this in a different way. We can say the force of attraction between A and B particles over here in the solution will be less. That is why escaping tendency will be more. And if the escaping tendency will be more, the vapor generated over will be more. That is why your actual vapor pressure of the solution comes out to be greater than that of expected vapor pressure of the solution. This is the expected vapor pressure of the solution. P naught A chi plus P naught B chi B. Yeah? Right? Or you can say this is the expected vapor pressure of the solution. Correct? P naught A chi plus P naught B chi B. Point number one. Point number two. Point number two. Let's assume volume of this liquid A is V1. Let's assume volume of this liquid B is V2. Let's assume volume of this resulting solution I'm representing by VR. Correct? If the force of attraction between A, B is less, can I say over here volume is going to be more? Absolutely. In case of non-ideal solutions, VR will be greater than V1 plus V2 because the force of attraction in the resulting solution is less. Okay? VR is greater than V1 plus V2. If I want to calculate delta V mixing, what is delta V mixing? That is going to be final volume minus initial volume. What is the final volume of the solution? That is VR. What is the initial volume of the solutions? That is V1 plus V2. V1 plus V2. And as I told you, VR is greater than V1 plus V2. If VR is greater than V1 plus V2, I'll say this value will come out to be positive. So remember, in case of non-ideal solutions showing the positive deviation, delta V mixing, you'll always get positive. You'll always get the delta V mixing as positive, correct? Similarly, after talking about delta V mixing, we can talk about delta H mixing as well. We can talk about delta H mixing as well. Remember, in case of the solution, in case of the non-ideal solution showing positive deviation, delta H mixing will be greater than 0. Delta H mixing will be greater than 0. So overall, this process is endothermic. What does that mean? See, first of all, what kind of interactions do we have right here in this liquid? We have got AA interactions in this container. Similarly, in this container, what all interactions do we have? We have got only BB interactions. And in this solution, what all interactions do I have? I've got AB interactions, correct? So first of all, when I'll mix these two liquids, I should get this solution over here. So the first process which should happen, that is the breaking of these force of attractions, or I can say breaking of these bonds, right? This is my first step. So first what should happen? This force of attraction should be broken down. And then once this force of attraction should be broken down, then only this bond is going to get formed over here. Yeah. First, this force of attraction should be broken down. Then only these two, this A and this B, they'll start interacting with each other. Yeah. I can say it like this. Now we'll understand. We know breaking of bonds, that is endothermic, and formation of bonds, that's exothermic, right? So over here, in this process, energy is absorbed. In this process, energy is absorbed. In this process, energy is released. In this process, energy is released, right? Okay, but remember, we know A force of attraction and BB force of attraction. Just give me a second, guys. AB force of attraction is less, right? I have shown it wrongly over here. It is less. AB force of attraction will be less than that of A and BB. Then only there'll be more vapors, right? Okay, that was my mistake, my bad. Okay, moving on. See. So first of all, when I'm mixing these solutions, in this solution, you have got A interaction. In this solution, you have got BB interaction. In this solution, you have got AB interaction, right? I mean, in liquid A, we have got only A interactions. In liquid B, we have got only BB interactions. In this solution, we have got AB interactions. Now, what is going to happen? These bonds are to be broken down first. Then only this bond has to be formed. Breaking of bonds is endothermic. Formation of bonds is exothermic, right? Right? Breaking of bonds is endothermic and formation of bonds is exothermic. We know it, correct? But people, we know A force of attraction and BB force of attraction, that is greater than AB force of attraction. So the amount of energy which is absorbed in order to break these bonds is greater than the magnitude of energy released when this bond is formed. Understand, the amount of energy which is absorbed during the breakage of these bonds is greater than the magnitude of amount of energy released in this formation of bond, this process, right? Due to which I'll say due to which I'll say this overall process is endothermic in nature. That's why I'm saying delta H mixing for this overall process comes out to be greater than 0, because the amount of energy to be absorbed in breaking of this bond is greater than the magnitude of amount of energy released when this bond is formed, correct? Right? Okay, perfect. Let's move on to one more point. I'm sure this is clear to everyone. Delta H mixing is greater than 0, yeah? Now talking about delta S mixing. Delta S mixing, right here again it's going to be positive. Delta S mixing is going to be positive because again you are mixing two liquids. What is going to happen to the randomness of the solution? Randomness of the solution will increase, and if the randomness is increasing, definitely your entropy is increasing, and entropy increasing means delta S mixing will be greater than 0. Okay, that's why. What is delta S mixing? Basically S final minus S initial, right? Okay, since when I add these two liquids, the entropy of the solution increases, so S final will be more than that of S initial. That's why this delta S mixing, it comes out to be greater than 0, correct? I'm sure this is clear to everyone again, right? Similarly, let's talk about delta G mixing. Remember, delta G mixing again over here is negative in nature, okay? Remember, delta G mixing over here again is negative, okay? In case of ideal solutions and all the non-ideal solutions, delta G mixing will be always negative. Remember this as well, okay? Let me know in the chat box if everything is clear till here. Let me know in the chat box if everything is clear till here, yeah? So that I can plot one curve over here. Let me know in the chat box fast. Let me know in the chat box fast. Yeah? Perfect. See guys, along this y-axis I'm plotting vapor pressure of the solution. Yeah, right here I'm plotting mole fraction along x-axis. The curve which we plotted in the last session, if you remember, correct? See, for example, chi A over here is 0, chi B over here is 1. Okay, let's assume chi B over here is 1 and chi A over here is 0, correct? Yeah, let's keep it like this. Let's keep it like this, right? So people, at this point, chi A is equal to 0, chi B is equal to 1. That means in the container, what do I have? I have got only liquid B in the container, okay? So if there is only liquid B in the container, that means B is present in its pure form and its vapor pressure is simply going to be P naught B. Let's say this is your P naught B, correct? Similarly, at this point, chi B is equal to 1. Sorry, just a second guys. This is chi A, right? I have written the reverse. This is chi A is equal to 1 and chi B is equal to 0. Yeah, correct. See, at this point, chi A is equal to 1, chi B is 0. That means at this point, I'm saying in the container, you have got only A in pure form. And if A is in the pure form, its vapor pressure is represented by P naught A. Let's say this point represents P naught A over here, correct? Now you can plot the curve. See, on moving from left to right, what is happening to the mole fraction of A in the liquid form in the solution phase? On moving from left to right, mole fraction is increasing. And if mole fraction is increasing, the contribution of A towards the total vapor pressure increases, right? This is the curve which represents your PA, contribution of A towards the total vapor pressure, right? If the solution finally which we are getting is ideal in nature. Similarly, this is representing PB, correct? This is representing PB, correct? And this curve over here, as discussed in the last session, it represents total vapor pressure of the solution, okay? But these curves only represent, these curves are only valid if the solution which I'm getting, that is ideal in nature, right? But in case of non-ideal solutions showing positive deviation, we got to know the observed vapor pressure is greater than the theoretical vapor pressure. The observed vapor pressure is greater than the vapor pressure of the solution calculated theoretically by means of Raoult's law, right? So if I need to represent the total vapor pressure of the solution, or I can say in order to represent the total vapor pressure of the non-ideal solution showing the positive deviation, the curve should be like this, yeah? The curve should be like this, correct? This represents the total vapor pressure of the non-ideal solution showing positive deviation, correct? Because we know in case of non-ideal solutions showing positive deviation, the total vapor pressure that will be greater than the theoretically determined vapor pressure, which is same as that of your ideal solution, yeah? Right? Okay. Now people, similarly, your PB value, it is definitely going to be greater than like this, and similarly, this curve will be like this over here. Sorry, I couldn't make it properly. It is like this, yeah? Right? So these curves, they basically represent your non-ideal solutions showing positive deviation, yeah? Correct? Well, Karthik is asking, sir, how delta G is negative? Karthik, it's simple, see. First of all, in this process, delta H is positive, right? Delta H is positive, and delta S is what? Delta S is positive as well, right? We have got delta G. Delta G is equal to delta H minus T delta S. Remember, in case of the solution showing positive deviation, right? Remember, the magnitude of T delta S is greater than the magnitude of delta H. Okay, remember the magnitude of T delta S is greater than the magnitude of T delta S. That's why your delta G comes out to be negative over here in this process. Yeah, remember this, correct? Now let's move on. Let's talk about the solution which shows the negative deviation. Understand properly what I'm going to say. Now I'm talking about the non-ideal solutions. Non-ideal solutions showing negative deviation, yeah? Non-ideal solutions showing negative deviation. Well, people, non-ideal solutions showing negative deviation. Understand, these are the solutions in which observed vapor pressure, that means the actual vapor pressure, comes out to be less than that of theoretical vapor pressure, which is calculated as per Raoult's law. Okay, or I can say it like this: the actual vapor pressure of the solution, it comes out to be less than that of P naught A chi A plus P naught B chi B. P naught B chi B, correct? Okay, right? Or I can say the actual vapor pressure of the solution is less than that of ideal solution. The actual vapor pressure of the solution is less than that of vapor pressure of the ideal solution, right? In case of what? In case of non-ideal solutions showing negative deviation, yeah? Right? Rifana, you can just drag the video back. It'll be a replay for you, okay? You can watch it afterwards. Right? Now people understand. What all things can we conclude from here? See, let's say this is the container which contains your liquid A, which is volatile in nature. The vapor pressure of this liquid A right here is P naught A, yeah? Similarly, I've got one more container which contains liquid B, which is again in pure form. The vapor pressure of this liquid B over here is P naught B. I'm adding them up in the same container, right? So over here you have got a solution of A and B. Over here you have got the solution of A and B. Let's say this was your liquid A. Let's say this was your liquid B. I added them up and I got the solution. And the total vapor pressure of the solution, as per Raoult's law, should be equal. It should be equal. I'm using the term should be equal. P naught A chi A plus P naught B chi B, correct? As per the Raoult's law is concerned, the total vapor pressure of the solution, it should be this much. But experimentally, it's calculated as P observed. And it's seen that P observed is less than PT. Or I can say P observed is less than P naught A chi A plus P naught B chi B. What can I conclude from here? Can I conclude something like this, that the amount of vapors over here above the solution are actually less. That's why the vapor pressure, that's why the actual vapor pressure comes out to be less than that of theoretical vapor pressure. Yeah? I can say something like this, right? Clearly I can say, right? Since the experimentally determined vapor pressure, the observed vapor pressure of this solution is less than that of theoretically determined vapor pressure, so I can clearly say the force of attraction between A and B over here is more than that of AA and BB. That's why escaping tendency is less. That's why the amount of vapors generated is less. That's why the observed vapor pressure, that's why the actual vapor pressure is less than that of the theoretically determined vapor pressure as per the Raoult's law. Yeah? Clearly? Correct? So I got to know something like this, that AB interactions are greater than, AB force of attraction is greater than AA force of attraction and BB force of attraction. Correct? Right? AB interaction is greater than AA interaction and BB interaction over here. That's why the amount of vapor generated over here actually is less than that of the theoretically expected thing. Yeah? Exactly, you can say that. right? Right? Now people understand. If I ask you delta V mixing, what is delta V mixing? Delta V mixing is final volume minus initial volume. Final volume, see, let's assume the final volume of this solution is VR. Let's assume the volume of the liquid A over here was V1, volume of liquid B over here was V2, volume of liquid B over here was V2, correct? So I'm saying delta V mixing, which is basically final volume minus initial volume. Initial volume is V1 plus V2, correct? It will be definitely negative over here. Why is that? Because force of attraction between A and B is more, due to which these molecules would have come closer. If these molecules would have come closer, I'll say the final volume of the solution will be less than that of initial volume. If final volume of the solution is less than that of initial volume, this term is definitely going to come as negative over here, which is what I call as delta V mixing, correct? Similarly, talking about delta H mixing. Remember, delta H mixing is again negative over here, right? Delta H mixing is again negative over here. What has to happen over here? See, in this container we have got A interactions, right here in this liquid we have got BB interactions, and right here in this liquid we have got AB interactions. First of all, these bonds have to be broken down, and then only this bond has to get formed, correct? Bond breaking is endothermic, bond forming is exothermic, right? Okay. Remember, since the force of attraction between A and B is more, so remember the amount of energy released during the formation of this bond, the amount of energy released during the formation of this bond is greater than the amount of energy absorbed during the breakage of these bonds, okay? The amount of energy released during the formation of this bond is greater than the amount of energy absorbed during the breakage of these bonds. That's why your overall delta H mixing, the overall delta H process comes out to be negative over here. So I'll say the overall process exothermic in nature, correct? Right? So remember this thing as well. And at the same time, if I tell you about delta S mixing, since it is mixing, in case of mixing, delta S comes out to be positive, and delta G mixing will be automatically over here as negative. Okay? So remember these things right here. Yes, Karthi, you can say it like that as well. No issues. Okay? Now people, let me summarize all this in the form of the curve. In the form of the curve again. See, first of all, this is the, along y-axis, this is the vapor pressure of the solution. Along x-axis, I'm representing mole fraction. Yeah. Let's assume right here chi A is equal to 0, chi B is equal to 1. Right here, for example, chi A is equal to 1 and chi B is equal to 0, correct? So right here we have got only B in the container. That means whatever is the vapor pressure, that's only because of B, which is what I call as P naught B. Which is what I call as P naught B. So over here, for example, this is P naught A, and I'm assuming P naught A greater than that of P naught B, correct? Now we will understand. If the solution which I got, the solution, this solution I'm talking about, the solution of A and B, correct? This is the solution of A and B. This is the solution of A and B. If this solution was ideal, then the curve should have been like this. Okay, then this curve represents PA, correct? This curve represents PA, which is the contribution of vapors of A towards the total vapor pressure of the solution, correct? If the net solution, resulting solution was ideal, then this line represents PB, correct? This line represents PB, and this line, it represents total vapor pressure of the solution if the solution was ideal. But the solution is showing negative deviation. The amount of vapor generated over here are actually less. Okay, vapor pressure actually is less. Vapor pressure of the solution actually is less. That means the total vapor pressure cannot be like this in case of the non-ideal solution showing negative deviation. It has to be below it, okay? Because the total vapor pressure of the solution actually is less than as was expected from the Raoult's law, correct? Okay, right? Correct. And at the same time, total vapor pressure can be only less. I can say total vapor pressure of the solution or the observed vapor pressure of the solution can be only less than that of ideal solution if the amount of vapors generated over here will be less. Okay, and when can be the amount of vapor generated over here be less? When there is more force of attraction between A and B, when the contribution of A towards the total vapor pressure will be less, right? So I can say PA value definitely is going to be less than that of P naught A XA, and over here P naught B is going to be less than that of P naught B chi B, correct? In case of non-ideal solution showing negative deviation, correct? So in case of negative deviation, This cannot be your PB. PB is definitely less than that of, this was PB, which was P naught B chi B, which was P naught B chi B if the solution was ideal in nature. This was PA, which was equal to P naught A chi A if the solution was ideal in nature. But this is the solution which is non-ideal, showing the negative deviation. So definitely PA as well as PB are definitely going to be less than that of P naught A chi A and P naught B chi B. So PB is actually will be like this, less than that of the ideal one. Similarly, PA is less than that of the ideal one. Correct? These are the curves which represent your non-ideal solutions showing negative deviation. Correct? Let me summarize everything now. Understand, this is important, okay? And any question can be asked from it, okay? Let me summarize it. Over here, I'm writing ideal solutions. Right here, I'm writing the non-ideal solutions showing, for example, positive deviation. And right here, I'm representing non-ideal solutions showing the negative deviation. Correct? Understand. In case of ideal solutions, first of all, first point, the observed vapor pressure, or you can say the experimentally determined vapor pressure, that's equal to theoretically determined vapor pressure. Okay, theoretically determined vapor pressure means the vapor pressure of the solution which we calculate by means of Raoult's law. Okay, or you can say the observed vapor pressure of this solution is equal to the ideal vapor pressure of the solution. PI, you can say it like this as well, right? Similarly, AA interactions are same as that of BB interactions, are same as that of AB interactions, right? Similarly, the next point, delta V mixing is equal to 0. Similarly, delta H mixing is equal to 0. Similarly, delta S mixing is greater than 0. Delta G mixing is less than 0. Correct? This is for the ideal solution. Now we have got one more, the ideal solution, which shows the positive deviation, in which the observed vapor pressure of the solution or the actual vapor pressure of the solution, that is greater than the ideal vapor pressure of the solution, or you can say that is greater than the theoretical vapor pressure of the solution as determined from the Raoult's law. So I can say P observed is actually greater than P naught A chi A plus P naught B chi B, which is only possible. This term is basically PA and this term is basically PB. So I can say in case of non-ideal solution showing positive deviation, your PA actually is greater than P naught A chi A and your PB actually is greater than P naught B chi B. Then only the total vapor pressure, the actual vapor pressure of the solution can be greater than that of ideal vapor pressure of the solution. Correct? So first of all, if the actual vapor pressure of the solution is more, that means AB interactions are less than that of AA and BB interactions. Correct? Similarly, delta V mixing we have observed is greater than 0. We have observed delta H mixing, it's again greater than 0, right? We have observed delta S mixing is greater than 0, and we have observed delta G mixing is less than 0, correct? All these parameters we have discussed, yeah? Now similarly, non-ideal solution showing negative deviation. In case of this, the observed vapor pressure of the solution will be definitely less than that of the theoretical vapor pressure of the solution, or you can say the observed vapor pressure of the solution will be less than that of ideal vapor pressure of the solution. And what is the ideal vapor pressure of the solution? That is P naught A chi A plus P naught B chi B. Yeah? Point number one. Point number two. When can be the actual vapor pressure of the solution less than expected? When PA will be less than P naught A chi A, when PB will be less than P naught B chi B. Yeah? And at the same time, since we are talking about the solution showing negative deviation, right? AB interactions are more than that of AA interactions and BB interactions, right? And at the same time, your delta H mixing is negative. Similarly, delta V mixing is negative. Similarly, delta S mixing, that is positive. And at the end, delta G mixing, that is negative. Anything can be asked from these parameters. You can let me know in the chat box if everything is clear till here or not. Let me know in the chat box if everything is clear till here or not. Yeah? Let me know in the chat box fast. These are all the parameters related to ideal and non-ideal solution, which you have to remember, and anything can be asked from these, okay? I'm sure your ideal and non-ideal solutions are done and dusted. Yes? Correct? Perfect. Perfect, guys. Perfect. So with this, we are ending the today's discussion. Yeah? Let me just give you the quick introduction about the NEET crash course, which we have started on the actual Vedantu platform. For the ones who have not enrolled in this yet, please do enroll fast, because it's going to be the last opportunity for you to get enrolled in this NEET 2021 crash course, right? This is going to be the last batch which will be starting right here for this NEET 2021 crash course, wherein I'll be training you personally for your chemistry, and will be completing the whole syllabus on the actual Vedantu platform, right? Apart from the syllabus completion, there will be test series involved in it, mock tests involved in it. We'll be training you personally, as I'm telling you, in all the subjects, your physics, chemistry, as well as biology. Yeah. And at the same time, apart from the syllabus completion sessions, there'll be some extra sessions regarding the tips and tricks by means of which you can solve the questions in lesser time, right? So people, do click on the Vedantu app. Just if it's in your phone, just click on it. If it's not, download the app, click on it. Just tap on the NEET crash course, and after tapping on the NEET crash course, do not forget to use this coupon code of WSNET. After using this coupon code, you'll be getting 30% off over here. And the batch is starting today. Okay, today it was supposed to start. You can join in tomorrow also, no issues at all. Link is there in the description box. You can click on the link, get added from there as well. And this is about the NEET 2022 batch, right? NEET 2022 batch is also starting. The link is there in the description box, and the batch is starting on 17th of May. Do not forget to use this coupon code if you want me to train in personally in this batch, yeah? And at the same time, there is one more link in the description box. That's for the Telegram. Do click on the link, get added to the Telegram group, and stay updated about the classes. And for the ones who have not liked the video yet, please do like the video, share and subscribe the channel as well. It was nice meeting you. Tomorrow I'll see you again, and tomorrow we'll be starting isomerism, okay? Tomorrow it is going to be the session for isomerism, right? As I told you in the last week, we'll be doing isomerism, solution and hydrocarbon parallel this week. So tomorrow it's going to be the turn for isomerism. Let's meet up tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all and love you all. Bye guys. Take care.